While atoms are the smallest fundamental unit of elements, we can actually break that down even further into smaller particles. These are called subatomic particles, literally meaning smaller than an atom. And there are three primary types of subatomic particles that you're going to need to be aware of that make up all atoms. There is the electron, and an electron carries a negative charge, a proton, which carries a positive charge, and a neutron, which is considered neutral and carries no charge. And what I'd like you to take a look at down at the bottom is not only the charges, but take a look at the relative masses of each of these. An electron is significantly smaller in mass than that of a proton and a neutron. In fact, protons and neutrons are very, very similar to, in terms of mass to each other, but electrons are much fundamentally smaller. In fact, if we take a look at the relative mass here, if the mass of an electron is considered 1, protons are going to be, protons and neutrons rather, are nearly 2,000 times the size of an electron. So protons and neutrons are much larger. I'd like you to know the relative size of each of these as well as their charges, because that becomes very important when we go through and try to determine the number of protons, neutrons, and electrons given an atom. So, like I said, the most important experiment, or one of the most important experiments here rather, is the Rutherford gold foil experiment. The Rutherford gold foil experiment, conducted in 1909, disproved the plum pudding model, which we discussed previously, which was that idea that there are volumes of positive and negative charge that are present in atoms. An atom is essentially empty space, just with positive and negative charges that are associated with it. So because of this, what Rutherford did is he designed a device, this alpha particle emitter, and basically what it does is it shoots little tiny atoms of helium in this little box. This box is made of lead because alpha particles are radiation, and radiation can be quite dangerous. But this little beam is shooting at some gold foil, and what he anticipated was that because atoms are essentially just empty space with positive and negative charges associated with them, that the alpha particles would go straight through. And so there's a detection screen that is around the gold foil, and what he anticipated was what you would see in the very first part of B there, that all of the alpha particles would go directly through the atom, none of them being deflected. However, what ended up happening was the one below that. Most of the particles did move through and go directly through the atom, but some of them were deflected. In fact, some of them were deflected so much that they came back towards the alpha particle emitter. Well, in order for something to deflect, it has to be hitting something. And so that gave Rutherford the idea that there has to be something small and dense, because first off, in order for deflections to occur, it has to be more dense than the alpha particle. So otherwise it would cause the nucleus or the particle to move. So whatever it's hitting has to be dense. In addition to that, it also has to be relatively small, because very few of the alpha particles actually deflected. If lots of alpha particles deflected, that tells you that whatever's causing the deflection is larger. And so as a result, you would get more deflections. And what this ended up telling Ernest Rutherford is that there is a small, dense component of an atom, which we know today as the nucleus. And so let's break down the arrangement of those subatomic particles in a little more detail here. All protons and neutrons are found inside of the nucleus. The nucleus, again, is a small, dense, positively charged center of an atom. It makes up 99.9% of the mass of the atom, because if you remember, protons and neutrons are nearly 2,000 times the size of electrons. Electrons are found in a large region around the nucleus, moving quickly and randomly. We also utilize the term nucleon to describe any particle that's found within the nucleus, so that would be considered protons and neutrons. Now, this model here on the right-hand side gives more of an example of a planetary model. That is the model of Niels Bohr, which is not exactly the best example, because as we discussed before, electrons don't orbit the nucleus like planets around the sun. They kind of exist in these regions that are called orbitals. Again, the orbital concept really is beyond the scope and sequence of this course, but it is important to give you an idea that what you're actually seeing on the right-hand side here is not 100% historically accurate based on what we currently know of the model of an atom. Now, atoms are generally neutral, and what that means is that they have no overall charge in the atom. Well, if in order for something to be neutral, the number of positive charges has to be equivalent to that of the number of negative charges that are associated with it. So in most neutral atoms, the number of protons is equal to that of the number of electrons. That is, the number of positive charges in the nucleus are equivalent to that of the number of electrons that are around the outside of the nucleus. Just to give you an idea of relative size, if the nucleus of an atom were the size of a baseball, then the diameter of an atom, that is, the relative size of the atom would be around 2.5 miles. So think about that in terms of how much empty space there is, and then also think about what atoms are in general. Atoms are mostly empty space, but atom makes up all matter. So by definition, all matter is mostly empty space. And that is amazing to consider when you think about when we actually look at things, when we're holding something that is mostly empty space, yet we see something solid. It's very, very weird to think about it, but when you get on a microscopic, submicroscopic level, things in terms of chemistry and physics get really, really funky and really, really weird. So, again, just to put some things into perspective there for you. So I'd like you to take a few moments, go through and determine the answers to these questions. How many of different subatomic particles carry a charge? How many electrons are needed to equal the mass of one proton? And atoms as a whole are neutral because of what reason? Take a minute, pause the video, and we'll come back and discuss these answers here in just a moment. Welcome back. Again, let's break some of these questions down. The first one says, how many of the different subatomic particles carry a charge? That is 2. Protons carry a positive charge and electrons have a negative one. How many electrons are needed to equal the mass of one proton? It's roughly 2,000. 1,800 electrons is perfectly fine. Again, it depends on the source that you're looking at, but as long as you're roughly within about 1,800 to 2,000, you should be in good shape here. And atoms as a whole are neutral because the number of electrons is equal to the number of protons. So just keep these fundamental ideas in mind as we continue to work through and understand the fundamental internal structure of atoms. So I'd like us to break out our periodic table because our periodic table contains some very, very important information. I know we haven't used it a whole lot yet, but it is one of the most fundamental pieces and tools that chemists use on a day-to-day basis. It breaks down and provides us with so much useful information that we really need to take into consideration what it is offering us. The first thing I want to talk about is what is called the atomic number. The atomic number is the number of protons that are present in an atom. It is also the same as the very large number at the very top of each individual element on the periodic table. So for example, the atomic number of hydrogen is 1. That means that hydrogen contains 1 proton. The atomic number for helium is 2. That means that helium contains 2 protons. 3 for lithium, 4 for beryllium, etc. The mass number is the number of protons plus neutrons that are present in an atom. This is information that you do not find on the periodic table. That is an information that you'll find or develop a little bit later on. But again, I want you to just understand what the fundamental concept of the mass number is because we'll be utilizing it a little bit later. For neutral atoms, the atomic number is equal to that of the number of electrons. Remember, the atomic number is equal to the number of protons that are present in an atom. And because atoms are neutral, the number of electrons will be equal to that of the atomic number, hence the number of protons that are present. And again, just to reiterate, the atomic number is also equal to the whole number present on the periodic table of elements. So if I look at potassium, which is K, number 19 on the left-hand side here, that tells you that potassium has 19 protons that are found inside of the nucleus. So an atom has an atomic number of 5 and a mass number of 11. Let's determine the number of protons, neutrons, and electrons in the atom. So the very first thing we want to take a look at and understand is the atomic number. Remember that the atomic number is the number of protons. And in a neutral atom, the number of protons will equal the number of electrons. So in this case, we can easily figure out the number of protons and electrons because both of those would be 5. Remember that the mass number is the number of protons plus neutrons. So basically, this ends up becoming a math equation. The mass number of 11 is going to equal the number of protons, 5, plus the number of neutrons, which is unknown. And so we just do a little bit of math there. We take 11 minus 5, and we end up with 6 neutrons. So again, as long as we understand the fundamental concept of where we're finding the atomic number and what the mass number represents, we can very easily calculate the number of neutrons and electrons that are present. Now, there are a variety of ways I may ask these types of questions. We'll look at different notations, but the fundamental concepts are still the same here. So make sure you take this information and apply it to some of the stuff we're going to look at here in just a couple of moments. Now, often, the mass number and the atomic number of a given atom are often specified using a specific notation. So the very first thing you want to look at is in the top left-hand corner, you see the mass number. Remember, that is the number of protons plus neutrons. So the number for A is always going to be greater than the number for Z because Z is just the number of protons. A here is going to be protons plus neutrons, which is the mass number, and Z is just the atomic number, which is the number of protons. So A will always be bigger than Z. And then the symbol just represents the chemical symbol of the element that's present on the periodic table. So we should be able to determine the number of protons, neutrons, and electrons from this notation, as well as be able to work backwards and utilize the notation to determine the number of protons, neutrons, and electrons as well. So given that information and the information that I've posted up here, I'd like you to take a couple moments and go through and try to determine the number of protons, neutrons, and electrons that are present in these particular atoms. I'll give you a few moments, pause the video, and then we will work through these together here in just a moment. All right, so I'm giving you a little bit of time to take a look at these. Let's look at the very first one here. We have F. If we take a look at the bottom left-hand number, remember that tells you the number of protons. So the number 9 indicates that there are going to be 9 protons that are present in that fluorine atom. Remember that the number of protons is equal to the number of electrons at this point in time because for now, atoms are going to be neutral, so we also have 9 electrons associated with that atom. Remember that the top left number is the mass number, which refers to the number of protons plus neutrons. Since we already have 9 protons, 10 neutrons are necessary to be added to 9 in order to equal 19. So that's how we go through and figure these out. We do it exactly the same for the other ones as well. When we look at the sodium atom, it has an atomic number of 11, so that tells me that there are 11 protons, which also means that there are 11 electrons. In order to have 23 as our mass number, we have to have the number of protons plus neutrons equal 23. Since protons is 11, neutrons has to be 12. And again, we follow the same concept here for this gold atom. We have 79 protons and 79 electrons based off of its atomic number in the bottom left corner. Its mass number is 197, so we need to add 118 neutrons in order to get that to be 197. So again, make sure that you understand how to read these symbols. In addition to that, be sure you also know how to make the symbols. These are going to read up and down, so make sure you take time, go through. I want you to write the symbol this time from this information. Just the reverse of what we just did. Take a few moments and we'll be with you in just a moment. All right, so if we take a look at these individually, the very first one has 13 protons. If I go and take a look at my periodic table and find the element with 13 protons, I'm going to find that it is aluminum. In order to figure out the mass number, which is in the top left corner, I need to take protons plus neutrons. So 13 plus 14 is 27, so that goes in the top left-hand corner of the symbol. 13 goes in the bottom left, indicating the number of protons, the atomic number. We have 17 protons, 20 neutrons, and 17 electrons. Again, I look at my periodic table. I find that 17 protons is chlorine. When I add 20 to that, I get 37. So that means that the mass number is 37 and is placed in the top left-hand corner. And then lastly, we have 82 protons. That is going to be lead. And 82 plus 118 is going to give us 200. So again, making sure that you can work back and forth from this information. There may be times where I give you little bits and pieces of all of this information. It's very important that you can fluidly work back and forth between determining protons, neutrons, electrons, and its symbol, and vice versa. So make sure you're very fluid in going through and determining that information.